Oh, hey, Algebra 2. Looks like you're back for more solving of equations. So here I have an equation I'd like you to solve. Solve the equation and state the number of types of roots that we have here. So we have an x to the fourth plus 625 equals 0. We want to solve that for x. We've done that with quadratic, and this might be something along those lines. But let's go back to what we just did, Descartes' rules of signs. So the first thing I would do is I count the number of sign checks, and they're both positive. So there's 0 sign changes, which means there's 0 positive real roots. Not good. Okay, let's try the number of negative real roots. So if I go to negative real roots, I put in a negative x for that. That's an even exponent, so it's going to come out positive, so I get 0 sign changes. So there's no negative real roots. So that means I have a total of 4 roots. They all must be imaginary. So let's see if we can find them. The first thing I would do is I would subtract 625 from both sides. So x to the fourth would equal a negative 625. Now, to get rid of the 4, I need to do the fourth root. So if I take the fourth root of x to the fourth, and I take the fourth root of a negative 625, I would have to have positive negative because I'm doing even roots. The fourth root of 625 is I. But I have a negative inside this root, which means I have imaginary roots. And that means I would have a positive or negative here, and I would have another set of positive or negative 5i. So those are all my roots, and I had 4 imaginary roots. Now on the assignment, you're going to have some quadratics. You should be able to solve the quadratic using the quadratic formula or factoring or whatever. You're going to have some other ones there where you want to factor. But I'm asking you to do this. So this is a review. The next set on the assignment is, again, just Descartes' rules of signs. How many possible positive roots, how many possible negative roots, how many imaginary roots? Go through that. Then the next thing we get to is this little thing called the lowest integral upper bound and the greatest integral lower bound. So let's start with the LUB, or the lowest integer upper bound. So according to the way we do this, if we use synthetic division to divide f of x by the quantity x minus b, where b is greater than 0, and we obtain a third row containing no negative numbers, then that b is the upper bound for the real roots of f of x. Now, I could put in a really high number and get that to work, but I'm trying to find the lowest b value that's going to work and make sure that all of those values have no negative numbers. Now, let's say we want to do the greatest integer lower bound. So if we, again, use synthetic division, divide f of x by x minus c, where c is less than 0, and we obtain a third row in which the numbers are alternately positive and negative, then c is the lower bound for the real roots of f of x equal to 0. In determining the signs alternate in the third row, zeros are ignored. So if there's a 0 in there, you ignore it. We just look for alternate. Okay, so those are the two things. Notice what it says here. We are using synthetic division. Synthetic division is going to be needed for these. So let's see if we can find a problem here. Okay, find the lower integral upper bound and greatest integral lower bound for the polynomial. So let's start with the LUB. Let's start with the lower upper bound. So the first thing I do is I set it up for synthetic division. So I've got a 1x to the 4, so I put down the 1, and then the negative 3, and then the negative 5, and then the 3, and then the 4. So now I want to do synthetic division with a 1. Now I'm going to modify my table a little bit. I'm not going to write every single number down. I'm just going to kind of do it, and then I'll write down the numbers that will be in that third row. So I'm kind of setting up my table a little differently here. It's going to be more of a table so we can follow the values. Okay, so the first trick in synthetic division is I drop the value down. So I got a 1. And then I take 1 times 1, and I add that to negative 3. Well, 1 times 1 is 1 times negative 3 is a negative 2. Negative 2 times 1 added to negative 5 would be a negative 7. Negative 7 times 1 added to 3 would be a negative 4. Negative 4 times 1 added to 4 would give me a 0. They're not all positives. One is not my upper bound. So let's try 2. Okay, I drop the 1 down. 1 times 2 is 2. 2 added to negative 3 is negative 1. 2 times negative 1 is negative 2. Added to negative 5 is negative 7. 2 times negative 7 is negative 14. Added to 3 is a negative 11. Negative 11 times 2 is a negative 22. Added to 4 is a negative 18. Again, not all positive. That's what we're looking for. So let's try 3. I drop the 1. 1 times 3 is 3. Negative 3 plus 3 is 0. 3 times 0 is 0. Plus negative 5 would be a negative 5. 3 times negative 5 is a negative 15. Negative 15 plus 3 is a negative 12. 3 times a negative 12 is a negative 36. Plus 4 is a negative 32. Again, not all positive. But we now have that second term as 0, so maybe we're making headway here. So let's try a 4. 4 times 1 is, bring the 1 down. 4 times 1 is 4, added to negative 3 is a 1. 4 times 1 is 4, added to negative 5 is a negative 1. 4 times negative 1 is negative 4, added to 3 is negative 1. 4 times negative 1 is negative 4, added to 4 is 0. Again, not all positive. We're looking for all positives in this row. So let's try 5. So I drop the 1 down. 5 times 1 is 5, added to negative 3 is 2. 5 times 2 is 10, added to negative 5 is 5. 5 times 5 is 25, added to 3 is 28. 5 times 28 is 140, added to 4 is 144. Those are all positives. So that means my least integral upper bound, my LUB, is 5. I will find no roots of this thing, no zeros, greater than 5. Okay, that's the first one. Now, let's look for the greatest integral lower bound. So again, I set up my synthetic division. So I have, 1, negative 3, negative 5, 3, and 4 again. But this time I need to use C, and the C had to be less than 0, so I've got to use negative numbers. So let's do negative 1. Oops. And I'm going to do it like I did last time, kind of as this table type thing. So 1, I drop it down. 1 times negative 1 is negative 1. Added to negative 3 is negative 4. 1 times negative 4 is a positive 4. Added to negative 5 is a negative 1. Negative 1 times negative 1 is a positive 1. Added to 3 is a 4. Negative 1 times 4 is a negative 4. Added to 4 gives me 0. Okay. These are alternating. I have a positive, negative, and negative, positive, but they have to go completely alternating. It has to be a positive, then a negative, then a positive, then a negative, then a positive, then a negative, right down the line. So this is not alternating. So let's try negative 2. Okay, again, I drop down the 1. 1 times negative 2 is a negative 2. Added to negative 3 would be a negative 5. Negative 2 times negative 5 is a positive 10. Positive 10 added to negative 5 is a positive 5. Negative 2 times 5 is a negative 10. Added to 3 would be a negative 7. Negative 7 times negative 2 is a positive 14. Added to 4 is 18. Notice they went positive, negative, positive, negative, positive. That's that alternating power. So that means that our greatest integral lower bound is a negative 2. So when I look at this particular problem, all of our values, all of our zeros, all of our roots, all of our solutions are going to be between negative 2 and positive 5. They all have to be located there. All 5 roots, or 4 roots. All 4 roots have to be located there. So that's how we do that. We do it through synthetic division. I think you're ready to go now on the assignment.